Thanks, Rajiv, for a great keynote. So our next speaker is Erik Stauffer, who is currently at Google. He got his PhD from Stanford in 2006, working with Professor Paul Raj. And since then, he has been at Besim and also at Broadcom, and he's now at Google. So he has done the journey from wireless to machine learning, and that's what he's going to talk about as well. So, Erik.
Okay, is that working? Well, thank you for that kind introduction. It's an honor to be here. It's a pleasure to be speaking to you today. I want to talk a little bit about where we are. I want to look to the future, but first I want to start in the past. And that's with Shannon's learning mouse Theseus. And like the Theseus' namesake from Greek mythology, he follows the maze and tries to find his way to the goal. And actually, Theseus is a learning algorithm that Shannon built out of the relays used for the Plano telephone service back in the 1950s. And Theseus is able to navigate this maze, test the walls, and figure out the path to the end. And if you take Theseus out and put him back in the maze, he'll use his memory from the previous experience to find the way to the goal without making any mistakes at all. In addition to that, Theseus will also detect if the maze has changed. So if Shannon moved the walls around, the mouse would continue on and hit a wall where there wasn't one before, and then relearn that area of the maze, and then continue on from memory once it reached a section of the maze it had, that it was able to navigate by memory. So not only is Shannon the founder of information theory, not only is he the key enabler of modern communication theory, but Shannon is active and contributing in machine learning back in these pioneering days. But I want to take a quick look at basically some parallel history that I kind of view from the machine learning history versus the, well, I guess I'm going to take a specific subsection of communication theory, and that's these forward error correction codes. But let's take first let's take a look at the machine learning column. So basically in the 1950s, there's the pioneering work. This is the perceptron and the cat neurons by Hubel and Wiesel. In the 1960s, we take multiple neurons and combine them together to form the Adeline and Madeline. That's the Woodrow and Hoff. And interestingly enough, Woodrow was also involved with the LMS algorithm, which is commonly used for adaptive equalizers. And then a lot of excitement led to, and I took this from Wikipedia, the AI winter, where basically excitement led to a bust, and algorithms were basically unable to deliver on what was at that time perceived as the promise. And I guess this is in part due to computational complexity issues as well as limitations of the amount of data that's available. But that's okay, things pause for a period of time. In the 1980s, things start to pick up again with the rediscovery of backpropagation and pooling. In the 1990s, there's a lot of progress with the support vector machine, recurrent neural net. That's kind of like the IIR filter of neural nets. And then in the 2000s, there's sort of another pause. And this is actually an interesting time for me because this is a time when I was looking at neural nets very exciting technology, but also limited in what it seemed like people were doing with them at that time. But then something has significantly changed more recently with this revolution of deep learning. And basically, I'll talk a little bit more about this, but basically we have a number of ideas that have come out more recently and a lot of success that folks are having. ReLU, Dropout, Batch Norm, AlexNet, and much, much more. Now let's take a look at this error correction code column. And basically, it's interesting to me that they start basically at the same period of time in the 1950s. The block codes, the Galway, BCH, Hamming, convolutional Reed-Solomon codes. Actually, Reed-Solomon is probably closer to 1960. In the 1960s, LDPC is invented by Gallagher and Viterbi decoding is discovered. BCGR is in 1970s, an enhanced receiver. And then concatenated codes, convolutional combined with block codes, are flying on the Voyager spacecraft. And then I kind of labeled the 1980s as the FEC winter, but basically we've taken block codes as far as we can go, and we've basically hit a limit to how close we can get to the Shannon bound with that technology. And it's not until the 1990s with the sort of the accidental discovery of the turbo code and its random interleaver, and then the sort of the rediscovery of the LDPC code, where things get moving again and we push on much closer to the Shannon bound. The turbo codes and LDPC codes are so successful that they're basically standardized and move into practical implementations within that decade. More recently, we've had the advent of the polar codes, which has made its inroads into the 5G control channel, which is very exciting, but it does seem like there's more potential for what the polar codes could do in the future. And now we're in this period, this decade now, where it doesn't seem like there's much happening with error correction codes. But I did color code this slide in a very particular way to suggest something. It does seem like sort of the advancement cycles between these two technologies have had some kind of correlated history. And it makes me really wonder what might be in the future, what might be around the corner for not only error correction codes, but communication theory and information theory in general. And so I guess my first postulate that I want to share with you is basically what is the future of communication and information theory? And I postulate basically that machine learning is going to have a major role to play. And one of the things that I'm excited about is that maybe more communication information theory results that we have that haven't been able to be implemented practically will be realizable in the not too distant future. But I want to take a quick look at some of the machine learning basics. This will be review for the machine learning experts. But this is basically a very simple neural net. Basically, it's implementing this f(x) function. I have some input x. I go through a couple of fully connected layers, and I produce this y. And maybe in this case, I'm doing some handwriting recognition, and I have this handwritten 2. And maybe I stack that array up as a vector, and I feed that into this machine. And I'm using this one-hot encoding at the receiver, or excuse me, at the output. And so basically, I don't have a 0, I don't have a 1, but this is a 2, and so this is the one-hot encoding vector for this input. And basically, how is this working? Folks, this is basically just linear algebra at some level. This fully connected layer that I've highlighted in blue is a matrix multiply. It's ax plus b. So from linear algebra, that's quite familiar. But that corresponds to basically a separating hyperplane where I'm taking some high-dimensional space and I'm slicing into half spaces on a per neuron basis. But then there's, of course, a twist relative to the linear algebra roots, and that basically is this max function. And this max function is known as the linear rectifier unit, or more commonly as the ReLU. And it has some interesting properties. Basically, it's very easy to evaluate. It's very easy to differentiate, except for at the origin where things are discontinuous, but practically that's of no concern. And it's interesting is that when I was looking at machine learning, a few decades ago, basically sigmoid and tanh were very common, and it's interesting to me that those have sort of gone out of favor and sort of been replaced now with this ReLU. And sigmoid and tanh are still used in some cases, but very specialized applications. Then we just repeat this process. We add another matrix multiply, we add another constant, we add another nonlinearity, and we continue on. Training is basically initialize the A's and B's with some random values, select some training examples, that's the X and the Y's, evaluate the error that the machine computes, and then use that error in the chain rule to backpropagate to update the A's and the B's. Basically repeat steps 2 through 4 until goodness occurs. But I want to talk a little bit about this deep learning revolution, and I think one of the key contributors to that was these image contests, or these image data set competitions. The first one was the CFAR10 data set, consisted of 60,000 32 by 32 color images, consisting of cats and dogs and vehicles. This particular cat and dog was not from that particular data set. And what this allowed was basically a competition, so that every year folks would submit their algorithms, and then the person or the team with the best result would get the bragging rights and a paper and an algorithm named after them. And each year that went by, progress occurred, and a lot of these heuristics that I'll have a little bit to say about were discovered. Things have moved on now to the ImageNet data set, which is basically more types, more images, and larger images. I wanted to also take a quick look at, just before the ImageNet and CFAR10 data sets were created, there was this construction of the convolutional neural net that's been very important as part of this deep learning revolution. So the first convolutional net comes from Jan LeCun, and this is basically the ELINet. And interesting to me is that this basically comes out of the AT&T labs in New Jersey. And so what's happening here is we have a fully connected layer on the output on the right, and we're basically prepending that with these convolutional pre-processing steps. In this case, he's doing handwriting recognition, so I have this letter K, and maybe I want to try to recognize that. And I pre-process that with these two-dimensional kernels, these two-dimensional filters, which I sweep over this image to create some new images. In this case, I have 6 filters, and I create 6 such images. I downsample that to form these smaller images, and then I have another set of convolutional filters. I downsample that again, and I feed that into my fully connected layer. So this is commonly known as the conv pool, fully connected structure. But my point for communications, though, is that this is actually a communications channel coding problem. There is some transmitter that's sending some letter, in this case the letter K, and it is the purpose of this machine to differentiate, to discriminate that that's the letter K in the presence of noise and interference. And that is a classic channel coding problem. Another structure that's very exciting, I think Tim O'Shea is going to talk a little bit more about this in the following talk, is this autoencoder for channel encoding. And basically this is a machine that's been shown to be able to learn how to communicate over a probabilistic channel that's shown in the center here. With the autoencoder structure, we basically feed some data to the input and the output. The machine learns how to adapt and form the Voronoi regions to determine how to send data through that channel. The dual problem is the autoencoder for image compression, and this is really exciting because people have been able to get world-class results with this structure, actually doing better than hand-tuned feature sets that were in algorithms before this revolution. So for example, what's happening here is I have some input. I have actually the same number 2 here. That's some image. Maybe it's 1,000 pixels. I'm trying to push it through this compressed representation. And so this compressed representation, basically, maybe it's only 100 bits, but it's an information bottleneck that limits how much information I can actually push through. And then I want to try to reconstruct this image at the output. And that this is basically a rate distortion problem from information theory. Batch norm is an important heuristic that's come out of the image competitions, and basically what's happening here is we're going to take the outputs of each of the activations and we're going to normalize them. We're going to compute their mean, we're going to compute their variance, and rescale those activations to be 0 mean and unit variance. Now that has the nice property basically of keeping the activations close to the origin where that nonlinearity occurs. But we don't necessarily know that that's a good idea, so we have a gamma and beta that we can use to undo that scaling if the machine chooses to do that, with those being learnable parameters. Max pool is quite simple. It's just take the maximum from each of these data sets. In communications, I learned this as basically as a downsampling operation. And then there's this notion of dropout, which basically I'm taking the neural net while I'm learning, and I'm taking some of the neurons and I'm removing them. And basically what this is doing is it's forcing the information to be spread out amongst the neurons, making sure that no individual neuron becomes too important. Folks have also noted that ensembling of neural nets basically gives better results than individual trained machines. And a dropout is basically one way of sort of simulating an ensemble in place. Okay, so I've talked a little bit about deep learning. I've talked a little bit about convolutional nets. I also want to talk about gradient boosting, or these so-called boosted trees. And basically these are a sequence of weak learners of, so for example, decision tree is a weak learner. A decision stump is a binary decision, and so you can have these forests of decision stumps. Errors are amplified for the next decision, and then this is sort of a successive refinement process. Adaboost is quite well known, and XGBoost is a popular open source implementation, and there are a lot of other implementations out there as well. But I wanted to go through Adaboost just briefly, and basically what's happening here is I have some samples, I have these X's, and I have these Y's. The Y's are these labels, and they may be labeled +1 or -1, and I'll go through a specific example in a moment. And I'm basically going to recursively build up some classifier with these binary decisions, these H functions. So there's this H function here, it's some binary decision. I'll find some scaling factor, and then I'll add that to the previous sequence of binary decisions to form some a resultant f of t function. The final decision basically is just to take the sign of that function to determine if the label should be a +1 or a -1. I initialize the algorithm basically by setting all the weights to uniform value, and then I find some H function, some binary decision in that space to minimize the error. I take that error and I plug it into this mysterious formula, which I don't have time to go through the details of, to compute this alpha parameter. And then basically I take that alpha, and then any of the samples that I get correct, I'm going to exponentially decrease their weight, their significance. Anything that I get wrong, I'm going to exponentially increase their weight and their significance. I'll renormalize and then continue on. But I'm going to give you a specific example. So here is my x's in my two-dimensional space. I've got my pluses and my minuses. And then maybe I divide the space with some H function like this. And then you'll see that I got all the minuses correct, but some of the pluses are wrong. So I'll circle those, and I'll compute some alpha and some epsilon. And then in my second iteration, basically, I'm going to take those pluses and I'm going to increase their significance. Maybe I find a new H function here where I get all the pluses right, but I get some of the minuses wrong. I'll circle those again. And I make those minuses even larger for the third iteration. And then basically what I want to do here is I'm going to find some other h function, and here you can see this particular h function is not that great. I actually don't get all the pluses right, or I don't get all the minuses right. But if I take those three decisions together and I scale them up with those alphas, basically I find a classifier that's able to classify everything in the space correctly. But my point of discussing this is basically, to me, with a history in communication systems, is this is very similar to the decision feedback equalizer. So basically, QAM slicing, for example, could be the h of x function. A BPSK slicer, for example, is a binary decision. That's a decision stump. A QAM slicer is a decision tree. And a gray-coded PAM, for example, could be a forest of decision stumps with being decoded with binary decisions. Training the equalizer could be training the weak learner, so supervised learning could be is analogous to using pilots. Non-supervised learning is sort of analogous to using data-directed online adaptation. And different weights and updates and error functions than the Adaboost for this type of equalizer, but there are also lots of different types, so I think it fits into that structure in a general sense. And so one of my messages to folks that have studied information theory and communication is that you're already a machine learning researcher. And my message to the folks looking at machine learning is that there's a giant body of communication information theory results that are there that are deeply applicable to the work that you're doing. So, for example, image classification, which we've talked about, is a quantization with noise problem, is a channel coding problem. Image compression with autoencoders, like we talked about, is a rate distortion problem. Language translation, for example, if I'm translating from, say, English to another language, I'm taking some message from some code book, say the English language, I'm converting it to some abstract representation, and then converting it back down into some other message in some other language to be sent on to some final destination. That's a decode and forward problem. Segmentation, which was talked about in the previous, I mentioned in the previous talk, is basically, folks have gotten really interesting and exciting results basically by using adaptive match filters. Data classification, boosted trees, like we talked about a moment ago, is analogous to successive cancellation with feedback. And then finally, I kind of want to argue that generative adversarial networks, or GANs, have some deep relationship with iterative decoding that's used in LVPC and turbo codes, where different networks are collaborating with each other to find some solution that's palatable to the other network. And then the last thing I wanted to kind of mention was this is sort of a summary of, I guess, my life experience. So your mileage may vary, maybe, there's some room for interpretation but my view is that there are basically two types of problems in the world, and I guess a couple of types of subtypes. So there's the convex problem, which from my training in information theory and communications was excellent if you could find such a thing, because you're looking for the global optima, and there'd be some fast method for trying to find it, or you'd have even better some analytical technique. And I put down the customer as science because basically I'm trying to maximize the SNR, trying to minimize power consumption, and the reward that I get is that I know that I have the best answer. I have the global optima, and I know that nobody can do better, and there's a deep satisfaction that comes with that. But unfortunately, the world contains a lot of these non-convex problems. And there's a lot of these convex problems where I'm looking for the global optima. And that's brutal in the sense that basically the only algorithm I have to get there is brute force, which is exhausting. And so basically what I find whenever I find myself looking inside this bucket, the first thing I really want to do is get out of this bucket. But fortunately, what's really exciting is there's this whole class of non-convex problems where all I really care about is some improvement to the status quo. I don't necessarily need the global optima, but maybe I still find it, but I don't necessarily know that I've done that. And that's where these machine learning techniques, I feel like, are really powerful and really well suited. So I put down here the customer's opinion because maybe I'm doing a recommender system. I'm trying to recommend some thing to buy or some movie to watch or something like this. And the customer doesn't necessarily care that I have the global optima suggestion for them. I have some improvement for them, and that makes them happy. So I basically want to summarize on that, basically saying that I think that ML, information theory, and communications are better together. I think there's a lot of commonalities and overlaps. Communications, I think, is an interesting application of ML. I think ML has a lot of interesting communication problems. And I think information theory is a fundamental basis for machine learning and communications. And so with that, I'll take any questions.
I wonder if the communication is an interesting application of ML. I wonder if you thought about, the fundamental problem of, treating it as an ML problem, because ML is actually a data-driven problem. It means that your data set, right? You have a training set and then you have a test set. In my mind, communication has to work everywhere, right? So, you don't want to, develop your communication algorithm with a training set, and then you apply it in a different environment where your training set is very different, and then it won't work, right?
Yeah, I think that, so I guess the question basically is that, is machine learning really applicable to communication systems?
I'm saying that you have to be really careful about how you apply it. So, a data-driven method versus an algorithm which trying to apply to all kinds of situations.
Yeah, I think my view on that basically is that, for example, as far as training goes, we have lots of data because we can do lots of autoencoder structures. So we can have generate as much data as we want to, and so in those sort of constructions, we're not really data limited. But the other side of the coin, there's lots of well-posed convex problems that construct inside of some of these communication systems. And I'm not suggesting that we necessarily, replace everything with some machine learning structures. There are some cases where there's a nice analytical form which we can still take advantage of. So I think there's a little bit of a combination of things that need to be taken into account there.
Any other questions? Okay, right.
And also, what do you think about the performance? Because now, you're replacing an algorithm with a giant neural nets, which could be very slow.
Yeah, so I guess the question is what do you think about performance? So I think, at this point it's still early days, so I don't think that I'm ready to replace my LDPC and turbo codes in my phone at this moment. But I think that there's still really exciting promise in the sense that there are all kinds of different situations where we don't have a Shannon bound, we don't know what the optimal thing to do is, and some of these autoencoder structures have shown us ways of being able to communicate on these sorts of channels for which we had no practical way of doing it before.
Okay, let's thank Erik again, and we'll have a coffee break and be back at 10:25.